Welcome to the course on advanced power electronics. So we'll cover today synchronous motor drives. The outline of presentation is types and application of synchronous motors, classification of synchronous motors, operating principle of synchronous motors, modeling of synchronous motors, control of synchronous motor drive like scalar control, vector control, direct torque and sensorless control, and case study of synchronous motor drive, that power quality improvement in synchronous motor drive, solve numerical problems and references. So coming to why synchronous machines, it's used for high efficiency. Synchronous motors can be designed to effectively operate over a wide range of speeds to provide the best drive for a wide variety of loads. And power factor correction, it can operate at leading power factor also to correct the other power factor as the other load is as shown in the figure. And reduce maintenance, constant speed means better quality product, and adjustable speed means lower power cost. So this is typically well wave of synchronous motor. So you can see the different parts of synchronous motor. Rotor, of course, typically of different design, silent pole as well as cylindrical nature. Low speed, very low speed, we use cylindrical silent pole, and high speed we use cylinder. You can see how the assembly of stack stator from core, typically of winding design. Then the rotor design. Now coming to application of synchronous motors. The application with the small rating starts with the electric organ, then starting use automotive type rating, then synchronous motor for step down gear, then 120 watt synchronous motor used in microwave or cooling fan, then synchronous motor positioning machine, and synchronous robots, actuators, hollow soft, high speed spindle synchronous motor, then clocks, record player, turntable, shaded pole synchronous motor stress motor trap ride, then medium rating air and gas compressor, vacuum pumps for medium rating, centrifugal fans, then medium rating centrifugal fans, blower, compressors and exhausters, then pulp and paper mills, ball mills, then medium rotor of synchronous motor used for large water pump, then synchronous motor used in clipper and refiner, chipper and refiner in pulp production process, and large high speed motors, and synchronous motor for lifting application like gearless. It can be designed for low speed, and three-phase medium voltage synchronous motor for offshore application, synchronous motor for centrifugal compressor in air separator, then high rating synchronous motor for crusher, grinder and mills. As you can see, quite large rating, and synchronous motor for in mills. Then ABB synchronous motor for pulp and paper application, optimized for refiner and wood grinder. Then municipal clean water pumping facility, 6000 horsepower vertical synchronous variable frequency drive up to 450 rpm. Then typically a pair of ancient carbon oxide air conditioning compressor powered by two antique 150 horsepower open frame synchronous motor. Then ball mill in my drive of 500 to about 8000 horsepower synchronous motor up to 120 to 400 rpm. High rating that GE synchronous motors is in use in reciprocating compressor, centrifugal compressor and pumps in different number of poles like 2, 4, 6 with 50 or 60 hertz variable frequency drive, and with the 5 to 100 megawatt in typically 4 volts, and voltage is 3.3 kV to 13.8 kV. So it is typically a synchronous motors of 3000 horsepower at 164 rpm with DPG enclosure driving a dual pinion ball mill at iron ore mine. Then synchronous condensers 169 megawatt MVA. Then synchronous motor used in mining. First, synchronous motor used in hot mills to withstand severe environment condition. Then high power blast furnace blower motor like a synchronous motor, and synchronous motor for railway application. Then Westinghouse C-belt type synchronous motor with DC excited motor in 1917. Now coming to the introduction, typically working when a rotor is excited with a DC and rotated, the resultant field also rotates so that sinusoidal voltage are generated in three phases and displays 120 degree time having a frequency directly related to rotor. And the element is three-phase two-pole synchronous motor has a stator with three coils which are 120 degree from each other. Although shown considered, they are actually distributed. So this is typically how the working. Current relation between magnetic field of the two poles rotating and current relation magnetic field with the two poles rotating magnetic field at 30 degree. How it is really, you can say with the current applied voltage and current, how it is typically gets shifting or movement at different angle, like a 60 degree angle, 90 degree angle. Now coming to classification of synchronous motors. So synchronous motors can be classified as wound field permanent or reluctance type. So wound field, brushless and reluctance. So the wound field motor has a distributed polyphase armature winding on the stator and DC excited field winding on the rotor. And the brushless construction is obtained when the rotor field excitation is provided by permanent. And synchronous reluctance motor uses an unexcited rotor having a silent pole or projecting pole. And the inverted construction is also possible, that is field on stator and armature on the rotor. Now coming to typically silent pole type. The silent means sticking out on projected out. The silent pole is a magnetic pole that is projected out of the rotor surface, and the silent pole rotor are slow speed machines varying 150 to 600 rpm. Silent type rotor has non-uniform air gap and two or four pole or more than that. Silent pole construction cannot be made strong enough to send the mechanical stress at higher speed. Now for high speed we have cylindrical type of machine. The cylindrical rotor is non-projecting surface type, and cylindrical rotor type rotor has a small diameter and large length, and the cylindrical rotor type rotor is used for high speed and has uniform air gap. A cylindrical rotor have a 4 or more poles. The high speed machine 1500 to 3000 rpm driven by steam turbine and use non-silent pole rotor due to following reason. Gives noise, less operational speed, and pull and flux is uniformly distributed along with the properties of proper sine wave and which give the better EMF. And this is a cylindrical rotor, how really field winding is distributed on, and we have even a damper winding. Now coming to equivalent circuit of cylindrical machine similar to the field MF, armature reaction MF, and rotates at synchronous speed and the same direction field. The resultant MF is produces air gap wave phi A, which induces back EMF. You can see the phasor diagram how the resultant is there and how the induced voltage with the applied motor. So now the field MF can be imagined to induce a voltage VF in the armature, which magnitude is equal to the open circuit voltage induced in the armature. It's known as the excitation of EMF. So based on the phasor diagram, the equivalent circuit is obtained and shown in the next slide. So the equivalent circuit, you have a RS XL leakage and the magnetizing, and then the equivalent the field excitation. So IF is the fundamental frequency armature phase current, which accounts for field MF in the sense that when flowing through the three-phase armature winding, it will produce the rotating EMF identical to the field MF. The magnetizing current is required to produce the air gap flux phi A, and the air gap flux causes the EMF E to be induced in the armature phase, and XM is the magnetizing reactance. The complete phasor diagram of the machine is obtained when RS and XL, which are respectively the per phase resistance and leakage reactance of the armature winding, are added. So you can clearly see how the phasor diagram, your typically the VF, E and ET terminal voltage, and the peak of rotating EMF produced by RMS current IF flowing through N upon P turns is F1 equal to 3 by 2 root 2 IF IN upon P, where N is the number of turns of armature per winding. The peak of the thing produced by DC current IF flowing through NF upon P turns per pole is given by F2 equal to IF into NF upon P, and the equating F1 with F2, so IF comes IF capital and root 2 NF upon 3 NA, and IF equal to NNF, where N is the constant for given machine and given N equal to root 2 NF upon 3 N. And this is typically the circuit how really have a reactance with the approximation, typically the excitation voltage, and then the equivalent of that the magnetizing and excitation, and the phasor diagram correspond to that Thevenin and Norton equivalent circuit of the same. So equivalent circuit X equal to XM plus XL and VF equal to JXM IF. So IF dash equal to XM upon XS IF equal to VF upon JXS, and IF dash equal to IF dash plus IS into V upon JXS. The XS is known as a synchronous reactance. So a per phase steady state equivalent circuit for non-silent pole machine, cylindrical machine is your RAXS into EF and V. So EF equal to VA minus IARA minus J IAXS, where XS equal to omega ELS known as synchronous reactance. The power output operation from voltage source, the steady state equivalent phase diagram of non-silent pole synchronous motor as shown here. Typically with the starting your EF, from your flux to EF, and then we have a resistance drop, reactance drop, and then the supply voltage. So power output becomes IA cos phi equal to V upon XS cos minus pi by 2 minus EF XS cos minus delta minus pi by 2. That comes minus equal to minus EF upon XS cos delta plus pi by 2 or equal to EF upon XS sin delta. And power input to the motor is PI equal to 3V AIA cos phi, that is 3 VAEF upon XS into sin delta. And power output from the shaft is PO equal to 1 poles into T into omega E, that is PI equal to PO, and therefore 2 upon poles T into omega E equal to 3 VAEF upon XS into sin delta. The torque here is of synchronous motor can be written T equal to 3 poles by 2 V upon omega E into AF upon XS into sin delta. Alternatively can be written T equal to pi by 2 pole by 2 square pi R F sin delta RF, where pi R equal to resultant air gap flux per pole and FF is MF of the DC field winding, and delta RF equal to electrical phase angle between the magnetic flux excess pi R and FF. And these are typically you can call it your power torque versus your power angle. You can see for motoring as well as for generating stable and unstable move. And this is typically the motoring and regenerative braking, how it goes positive and negative torque, and phasor diagram corresponding to motoring and generating. Then typically the angle delta dash between the phasor of IF dash and IS in relative rate of following delta dash equal to pi by 2 plus pi minus phi. As you can see, IF dash at the minus delta also as a current source. So now V equal to JXS IM dash equal to JXS at the in bracket IS at angle 0 plus IF dash at the angle minus delta dash, and that is equal to XS IF dash sin delta plus JXS in bracket IS plus IF dash cos delta, and power del of PM equal to 3 real part of IS V star, that is equal to 3 XS IS IF dash sin delta, and torque developed T equal to PM upon omega ms, that is 3 XS upon omega ms IS IF dash sin delta dash. Alternative expression for torque is obtained T equal to 3 into XS upon omega IS IF dash cos in bracket delta minus phi, and the pull out torque is T max equal to 3 XS upon omega IS IF dash. And this is the torque typically from current source. So how the torque and power angle range for typically motoring and generating its goal torque T dash of a synchronous machine by current fed source. And this is the phasor diagram for motoring and brake operation, regenerative operation with the your voltage and excitation voltage, your excitation current and magnetizing current and supply current. So coming to now typically for silent pole motor, on the rotor we have silent pole. Normally we have a higher number of poles, projecting poles, but here symbolically sold as a 2 pole. So the silent pole motor has a filled poles projecting out from the rotor core, and it is characterized by different air gap reluctances in direct and quadrature axis, and tendency of rotor poles to align with rotating air gap wave at a position of minimum reluctance or maximum flux causes reluctance torque to be produced. In addition to this, reluctance your synchronous torque is also present like in a cylindrical rotor motor. And these are typically your phasor diagram of silent pole motor, that we have a supply voltage and I the axis and Q axis current and reactance drop, and EF addition of that, and the different phase angle and current phasors like correspond. So power output from phasor diagram we can have silent pole IA cos phi equal to IAQ cos delta minus IAD sin delta, and power input to the motor Pi equal to 3V IA cos phi, that is 3A VA in bracket IAQ cos delta minus IAD sin delta. Again from phasor diagram we can write IAD equal to VA cos delta minus EF upon XD, and IAQ equal to VA sin delta SFQ. Therefore PI equal to 3 VA in bracket VA cos sin delta upon XFQ cos delta minus VA cos delta minus EF upon XD sin delta, and finally we get PI equal to 3 VA EF upon XD into sin delta plus 3 VA square XD SXD minus SQ upon 2 SXD SQ into sin delta. The power output from shaft is equal to P equal to 2 upon P T omega Pi neglecting loss, therefore T equal to 3 pi by 2 omega in bracket VA EF upon XD sin delta plus VA square XD minus SXD minus XQ upon 2 SXD XQ to sin 2 delta, or T equal to 3 P by 2 1 upon omega I pi S pi F upon LDS sin delta plus pi S square LDS minus LQS divided by 2 LDS LQS into sin 2 delta. This is the typically torque versus angle power angle characteristic for leading and lagging mode of synchronous machine for motoring and braking mode. These are the phasor diagram corresponding to motoring and braking mode. So coming to tangent operation. So during tangent operation of a change in load torque, the rotor oscillates around the synchronous speed and the required torque angle delta also oscillate before reaching steady state. So similar oscillations are produced for a disturbance in a voltage or field excitation or the frequency. The damper winding provides the damping to these oscillations. For some time the rotor losses synchronous to the tangents. So the torque during the loss of synchronous is called pull-out torque and given as a equation delta equal to plus minus 90 degree, and the pull-out torque T max equal to 3 by omega P by 2 EBA FXD. Now coming to advantage. As compared to DC motor, these motors do not have limits of maximum speed, voltage and power rating, and these motors have lower weight, volume, inertia and maintenance frequency as compared to the same rating DC motor. So similar, since the air gap flux is not solely produced by the magnetizing current drawn from the armature, a larger air gap suiting the mechanical design can be chosen, and the synchronous motor can operate at higher power factor and full load efficiency than induction motor, and the wound field synchronous motor can be designed for a higher power rating than the induction motor. Now coming to scalar control of synchronous motor. The scalar control is of limited use because of it is different for the rotor track arbitrary changes in the frequency of the applied armature voltage, and in addition the starting is a major problem which is accomplished by using the damper winding. So during tangent the rotor of synchronous motor must remain in synchronous with the stator flux to develop the torque, and the scalar control methods are easy to implement, but the response of motor becomes sluggish and poor. Now coming to variable speed operation. So the synchronous motor, the speed can be controlled by controlling its supply frequency. With the variable frequency control, the synchronous motor may operate in two modes. True synchronous mode, the speed is controlled in open loop by precisely controlling the frequency, and self-control mode, the frequency is varied according to variation in rotor speed in closed loop, so that the armature field move at the speed same as the rotor. The basic control strategy is to operate the motor at constant flux below base speed and at the reduced flux or constant terminal voltage above the base speed, and the variable frequency control synchronous motor with self-control essentially work as a commutatorless or a brushless motor. However, its control is not that simple as a DC motor, because the synchronous motor operates without eliminating the armature reaction. So consequently the flux does not depend upon the field current alone, but also on the armature current. So further, the power factor control imposes additional constraint on the drive operation and control. Now coming to true synchronous mode of synchronous motor. So in the true synchronous mode, the supply frequency is controlled from an independent oscillator, as in the case of an induction motor, and the speed can be controlled precisely in open loop by precisely controlling the frequency, and the motor accelerates to follow the changes in frequency, and when the frequency reaches a new setting, the machine settles at a new speed after oscillation, which are damped by the damper winding. So in practice, the true synchronous mode of operation is employed only with the voltage source inverter, and as in the case of an induction motor, the common control strategy is to operate the motor at a constant air flux up to base speed and at a constant terminal voltage above the base speed. The constant air gap flux operation below base speed is achieved by operating the motor with constant V by F ratio, and this is truly synchronous mode that we have a frequency, and with the delay reference frequency or speed we have a delay, and from flux control we generate the reference voltage, and for voltage control we use the control rectifier to control DC voltage, and for frequency control we have an inverter, and we can run even a multiple synchronous motor also with this in this true synchronous mode. The frequency is the same for, and speed will be also same for all the motor. So now coming to constant voltage variable frequency operation. So from Faraday's law, the air gap component of the armature voltage in AC machine is proportional to the peak plug density in machine and electrical frequency, and thus neglecting the voltage drop across the armature resistance and leakage octane. Armature voltage can be written as V equal to Fp upon F rated into P, B peak upon B rated into V rated. So V is the armature amplitude of armature voltage, F is the operating frequency, B is the peak plug density, F rated, B rated are the corresponding rated value. So coming to the speed of wound-filled synchronous motors can be precisely controlled by frequency control and can be made independent of variation in supply voltage, field current and load, thus keeping V equal to V rated. And this equation can be B peak equal to F rated upon Fp into V rated. This demonstrates the constant voltage variable frequency operation. In this mode, the machine operating in saturation at rated voltage and frequency, and any reduction in frequency will lead to further increase in plug density. So higher plug density will result in increased core loss and higher machine current. So therefore, for frequency less than or equal to rated frequency, the machine is operated at constant again the V equal to V rated. This makes this V equal to F E upon F rated V rated, V upon F equal to V rated upon F rated. This is constant voltage per hertz operation, and this constant V by operation it is typically maintained from rated frequency to the low frequency at which armature resistance drop becomes significant component of the applied voltage, and for frequency is higher than the rated with the voltage at its rated value, the air gap plug density will drop below its rated value, and thus to maintain the rated plug density the voltage have to be increased, which may result in insulation failure. And therefore for frequency above the rated frequency the terminal voltage is kept at a rated value, assuming that the machine cooling is not affected by the rotary speed. The maximum permissible terminal current will remain constant at its rated value I rated. Therefore, for the frequency below the rated frequency, the machine power will be proportional to Fp, V rated, I rated. And this is the, you can see from the characteristic that constant torque operation, and the typically above rated we have a constant power operation. So below base speed the torque is constant, above base speed the power is constant. So operating regions as the torque equal to power upon omega E, the omega is proportional to Fp, therefore the maximum torque will be proportional to the V rated, I rated, which is constant. So similarly for frequency above the rated, the maximum power will be constant as V rated, I rated, and corresponding to maximum torque will be then vary inversely with the machine speed as V rated, I rated upon omega E. So maximum operating speed in this region will be determined by the maximum frequency of power electronics circuit or by speed to which the rotor can operate safely. Now coming to topology of true synchronous mode. So we have typically a 3-phase thyristor bridge with the control of DC link voltage to maintain a that's the DC what we want for inverter, and the typically controller for deciding the frequency fitting the synchronous motor. So this is voltage source in required synchronous motor die, and the control is with the reference frequency. With the delay we get the frequency, and with the control we get the typically a voltage control, and then the frequency control we control the field current, and from firing angle we control typically, and from frequency we control the VSAL. And this is with the typically cycle control. So similarly with the reference frequency we get the frequency, and then the voltage goes to cycle converter control as well as the frequency V by L, and we control with the 5 even if your field current. It is similar to the matrix converter scalar control. So we have a reference frequency, then delay frequency we get the voltage proportional to, and then a control rectifier, and then control the matrix. So now move to self-control mode, which is really used in the industry nowadays. So in self-control mode, the rotor speed changes, the armature supply frequency also change proportionally, so that the field armature field always move the same speed as the rotor. Consequently, the armature field always move at the same speed as the rotor. It does not pull out of a step with the step change in torque or frequency and control from an independent oscillator. So the accurate tracking of speed by frequency is realized with the help of rotor position sensor, of which there are two types of rotor position encoder, armature terminal voltage sensor. So in rotor position encoder, the firing pulses to converter switches feeding to the motor are delivered, and the direct axis of voltage axis of rotor makes the certain predetermined angle with the axis of armature phase. As the switches are fired at a frequency proportional to the motor speed, the frequency of voltage induced in the armature is proportional to speed, and the desired tracking of the speed by frequency is also realize when the converter frequency is made to track the frequency of the induced voltage, and induced voltage is obtained indirectly through armature terminal voltage. So in the self-control mode, the motor cannot adjust the torque angle mechanically, as in case of conventional operation. The torque angle can be adjusted electronically, and it provides additional controllable parameter and thus the greater control. So the self-control applicable to all variable frequency inverter, namely voltage source inverter, current source inverter, current control pulse width modulator inverter, cycle converter. So difference compared to conventional operation is that the frequency is not available anymore as independent control available. So when the motor is fed from a voltage source inverter, the voltage is changed as a function of frequency, and voltage is changed to obtain operation at a constant flux below the base speed and at constant terminal voltage above the base speed. The control block diagram of a closed loop speed control fed VSI is shown in the next slide. So you can have a reference speed, you have a feedback speed pump sensor, then the error goes to the speed control which decides the power angle, and from speed you get the frequency and voltage, and with the angle we are able to get angle, frequency and voltage for voltage source inverter to control the synchronous motor feeding the motor. So coming to the converter VSI, the block diagram shows the frequency and output voltage of the inverter change as a function of speed, and in the steady state an increase in speed command will produce a speed error, increasing the torque angle and causing the machine torque to exceed the load torque. As the rotor speed increases, the inverter frequency and voltage will also change. So steady state is reached when the motor torque balances the load torque and the actual speed is close to the desired speed, and the change in operating point is brought on by the change in the torque angle and not the frequency, as in case as control from an independent oscillator. In the case of on-field motor, the field current can also be controlled in addition to the torque angle control. So this is typically how the voltage source inverter we feed the rectifier with capacitor filter, and how we have a voltage source inverter. Large rating we use GTO, medium rating we use the IGBT feeding the motor, and this is the thyristor control we typically for the controlling the DC link with the LC filter, and then we have an inverter with the large rating GTO, and medium rating we use the IGBT. This is typically what we are saying, the rectifier with capacitor filter and IGBT inverter, and then the typically again the thyristor converter LC filter with the IGBT inverter. Now coming to here current source inverter. In case of when a motor is fed from a variable frequency current source, control of speed and torque is achieved along with the control of flux and power factor. We have a reference speed, we have a speed pump sensor, so we have a controller which decides from error to DC link current, and we sense the DC link current, and that error goes to the fire angle control of thyristor converter which decide the DC link current, and from this same speed we go to the frequency, and with the power angle we go to the current source inverter control. That's also called angle control of current source inverter. So we have here the thyristor converter deriving with the inductor as a current source, and we have a thyristor converter inverter feeding the motor, because the commutation can take place even from the vacuum of the motor. So this is, we have a thyristor converter for as a large inductor, and we have a IGBT base with the series diode inverter feeding a synchronous motor. Like, of course, because IGBT don't have reverse voltage blocking capability, so we have to connect a series diode which takes a blocking voltage across it. So, and then we have a on GTO with the PWM, low frequency PWM with the capacitor filter, and we have a again typically the your current source and then the IGBT based current source inverter in operating PWM. So both operates in PWM. IGBT can operate high frequency so that the capacitor can be reduced on the motor side, and GTO operates at low frequency, so you can get a unity power factor on both the sides. Now coming to topology for self-control mode. So here, we have a typical speed sensor, we have a feedback, and from error get the power angle, then from speed we get the frequency and voltage. With these we go for VSI control, and of course we control the thyristor converter for field angle, field current control. So that with the perfect control, so we have a speed and feedback speed, then speed control rectifier how to feed the rectifier, then we have a phase shifter with the speed, so we get to the inverter, and of course we have a power factor computation, so perfect command which is shifted with the inverter control. Of course we have a flux sensing as well as the position sensing here, and that we have a CSI fed synchronous, and also we have a reference speed, feedback speed, the speed arrow goes to the DC link current sensing, and DC link current feedback is given. That decide the power angle of the control rectifier, which decide the current source current, and then from power angle and speed we get the frequency, and the angle and frequency decide the gating of the current source inverter, and of course thyristor converter decide the typical the field current. So this is typically a line converter inverter which are very popular for synchronous motor drive high rating, especially up to even you can call it a 100 megawatt drive. So we have a symbolically we may use the mini bridges. So we have a thyristor converter driving current source, we have a reference speed, we have a feedback speed, maybe from position or normally from terminal voltage sensing, and then with this we decide the DC link current and feedback current. We get the rectifier control power angle, and on inverter side we again have a position sensing, and with well synchronized with that we give the getting to the your line commutator inverter, which has commutated from the synchronous motor back. So this become a very economical and give the performance control DC motor, and this has been very popular even before the vector control came to operate this motor in self control mode. So this is by torque angle control, and we again have a position sensor and then the DC link current sensor in the same way, but here with the phase shift angle control we can control the inverter. So this is a basic concept of margin angle control. So we have a because inverter is line converter, so we have a margin angle control. So we have a speed sensing, then reference speed, then it will control decide the DC link current, and from sense DC link current we control the converter rectifier to as a current source with the inductor. And then we take a current and voltage sensing, and we sense the current, and from this gain we control have a voltage control oscillator to giving a control for inverter. Of course the flux sensor decide the field current. These four cycle converter for drive-ins. So we have a reference speed, then we have a sense speed, we have a decide by armature current for cycle converter reference, and then typically from the four flux we go to the flux field current control, and from the same also we have a reference flux, and of course we have a from speed we have a cos theta sin theta with the we get the three phase reference, and which we really amplitude of current already there, and we have an angle also, so we calculate three phase reference current to control the cycle current. Similarly, same control is used for matrix converter. So coming to advantage of self-control mode, the operation of typically synchronous motor in the self-control mode eliminates the hunting and stability problem. It permits the realization of versatile control characteristic of a DC motor without the limitations associated with commutator and buses. So limits on maximum speed, limits on voltage and power and frequency maintenance. So the power factor of a wound-field synchronous motor can be controlled by controlling its field current. It has the following advantage: minimize kVA rating, minimize cost, minimize losses of variable frequency supply, and maximize the motor power factor while reducing its losses. So by operating the machine at leading power factor, the inverter thyristors can be commutated by armature induced voltage, also known as load commutation. The load commutation reaches the frequency range of a current source inverter and a cycle converter. A load commutation and the associated benefits are available with the per magnet drives also. The advantage of cell control over the other benefits associated with load commutation are eliminates the need for commutation circuit, minimizes cost, minimizes weight, minimizes volume, and reduces losses in inverter. In disadvantage of cell control, the only disadvantage of cell control motor is compared to the DC type is their complex control. Moreover, it cannot operate even at unary power factor because of line commutation. It has to operate in leading power factor mode. Now, coming to commutatorless motor, the self-control synchronous motor platform inverter produces a steady torque at all speed, as in case of DC motor. The rotor position sensor and inverter perform the function same as the brushes and commutator in DC motor. Unlike the DC motor, the self-control drive does not have to operate at delta dash equal to 90 degrees because it does not have a problem with the sparking. Therefore, delta dash can be chosen at a suitable value to satisfy other person's requirement. And because of the similarity in operation with the DC motor, the inverter fed self-controlled synchronous motor drives on in a slide is known as a commutatorless DC motor. This typically we have a field control separately for above base speed, and we have power angle with the position feedback. We had angle control and frequency control for this self-control synchronous motor. The self-control synchronous with cycle converters, we have a similar concept in cycle converter. Coming to load commutation, so one important reason for preferring the synchronous motor drive over the squirrel cage induction motor drive for high speed and high and medium power ratings is the load commutation. The load commutation is made possible because of ability of synchronous motor to operate at leading power factor. And the load commutation has been employed for current source inverter and cycloconverter. And the circuit diagram of load commutator drive using a inverter is shown in next slide. So you have a thyristor converter, two thyristor converter, one work as a current thyristor rectifier to derive a current source, and then you have another inverter converter driving the motor. Of course, in regenerative braking, it can feed the power back to the same. So inverter will catch the rectifier and rectifier will convert according to firing angle control mode. So the DC supply for inverter is obtained from a 6 pulse fully controlled rectifier, and together with the link inductor LD, it can be considered to constitute a current source for the inverter. And the link inductor reduces the ripple in the link current ID and prevents the inverter and rectifier from interfering with each other operation. The synchronous motor has been modeled as a three-phase set of sinusoidal voltage with RMS value V behind the commutating reactance LC per phase. So due to the very short duration of commutation tangent, the commutating inductance is equal to the subtangent inductance of a synchronous motor, and the phase voltage is Vn, Vpn, when Vcn are the voltage induced in the armature due to the flux linking the armature, the air gap flux and armature leakage flux. And since the armature resistance drop has been neglected, these voltages are equal to the terminal voltage. So the inverter is similar to the current source inverter, except that the commutation circuit consisting of diodes and capacitors is absent, and the functional of the commutation circuit is now performed by the induced voltage Vn, Vpn, Vcn, and thyristors are fired in the sequence of their numbers in with the 60-degree interval, and turning on an odd numbers thyristor causes commutation of previously conducting odd number thyristor. The same is true for twin number thyristor. Each thyristor conduct for 120 degree and only for two thyristor conduct at a time, neglecting the commutation interval, and three thyristor conduct at a time. And the waveform of all 6 line voltage are shown in the next slide. So transfer of current from an outgoing to incoming thyristor can take place when the respective line voltage is positive, so that it acts as to forward bias and reverse bias the increasing incoming and outgoing thyristor respectively. So this is typically the firing angle control. So you can see how your margin angle, advance angle, and overlap angles are there, and all 3 phase currents are there typically getting pulse correspondent. So firing angle greater than 90 degree, initially thyristor T5, T6 are assumed to be conducting. So DC link voltage VD will be then VCB, and at alpha T1 is fired, and due to commutating inductors, current cannot be transferred instantly from T5 to T1. So DC link current ID is assumed constant during this interval. And this is the mode when typically all 3 phase conducting commutation, 3 thyristor, 2 from 1 from negative group, 2 from positive group. So since the line voltage VSC is positive, it reduces IT5 to 0 and increases IT1 to ID during the commutation overlap angle, and at T5 turn off, T1 and T6 start conducting, making VD equal to VAB. Since the average value of VD is negative and ID is positive, the power flows from the DC link to the machine, giving motoring operation. And for alpha less than 90 degree, the average value of VD is positive. Since the direction of ID remains unchanged, the power flow from the motor to DC link, the inverter works as a rectifier, and the machine regenerates. And for mathematical analysis of inverter, thyristor 1, 5 and 6 are to be conducting during commutation, and from the equivalent circuit IT1 plus IT5 equal to ID by the differentiating it DIT1 equal to minus DIT5 upon DT, and from equivalent circuit LC DIT1 dt minus VSC minus LC DIT5 upon DT equal to 0. Since DIT1 upon DIT equal to minus DIT5 upon DT, therefore DIT1 upon DT equal to VSC up to LC. So VAB equal to root 3 root 2 V sin omega t, and VSC equal to root 3 root 2 V sin omega t minus 60. So DC link what is given by VD equal to minus LC DIT 1 upon DT plus VAB equal to VAB minus 0.5 VSC. The commutation period and at equal to omega t equal to alpha plus 2, and IT equal to IT5 equal to 0 and IT1 equal to ID. Therefore, by integrating equation of DIT1 upon DT equal to VSC upon 2LC and substitution, we get ID equal to 1 upon 2 omega LC integration alpha plus pi by 2 to alpha plus pi by 3 plus mu VSC d omega t, and after substituting value of VAC, तो cos alpha minus cos alpha plus mu equal to 2 omega LCID upon root 6 PD V, and mu is the commutation overlap angle, and beta is the angle of lead known as commutation lead angle with the respect to instant of VAC CJ to positive. So beta equal to 180 minus alpha, or alpha equal to 180 minus beta. Therefore, cos alpha minus cos alpha plus mu equal to cos alpha cos 180 degree minus beta minus cos 180 minus beta plus mu equal to 2 omega LCID upon root 6 VC. So cos beta minus mu minus cos beta equal to 2 omega LCID upon root 6 V, and after turn of T5 remains reverse biased until VAC equal to 0 and decreasing it in this duration. If this duration denoted by gamma known as margin angle, then gamma equal to beta minus mu, and for safe computation gamma should be greater than omega TQ, where the TQ is the turn of a time of the thyristor, and when the overlap angle is 0, the fundamental component of currents leads to respective phase voltage by an angle beta. The effect of commutation overlap is to delay the fundamental component, and the delay is approximately 0.5 times mu when the current waveform is assumed to be trapezoidal. So in the presence of overlap, the fundamental component leads to induced voltage by beta minus 0.5 mu, and hence the power factor angle of the machine is phi equal to beta minus 0.5 mu leading. For same computation, beta must be greater than mu, hence will always be positive. This shows that with the load computation, the machine always operates with the leading power factor. And for 6-step current waveform, IS equal to root 6 upon pi ID, and IRMS equal to root 2 upon root 3 ID. The effect of overlap is to phase shift IS by 0.5 mu. However, its magnitude remains approximately the same. So when commutation overlap is 0, the average value of PD will be then PD equal to 3 root 6 upon pi V cos alpha. So the effect of commutation overlap is to change the DC link voltage from VAB minus 0.5 VAC, and the change in the average value of DC link voltage is given UD equal to 3 upon pi alpha plus pi by mu to alpha plus pi and 3 plus mu 0.5 VAC given, that comes 3 root 6 V upon 2 pi in bracket cos alpha minus cos alpha plus mu. So substituting value, the DC link voltage UD equal to 3 upon pi omega LCID. So average DC link voltage in presence of commutation VD equal to 3 root 6 V upon pi cos alpha minus 3 upon pi in bracket omega LCID, and the power input to the motor is Pin equal to minus VDID, and power developed by the motor is PM equal to Pin minus 3 IRMS RS, or equal to minus VDID minus 2 ID square RS. So therefore the torque developed by the motor is T equal to PM upon omega m, that is minus 1 upon omega m in bracket VDID plus 2 ID square RS, and where omega m is the motor angular speed, also PM equal to 3 in bracket VIS cos pi minus IRMS square RS, and T equal to PM upon omega, that is minus 3 upon omega in bracket VIS cos pi minus IRMS square RS. Both torque expression are valid for motoring and braking operation. Now coming speed control below the base speed is obtained by the control of the rectifier output voltage VD. An increase in the rectifier output voltage with the beta held constant increases the DC link current ID as a result, and IS and the motor torque increases. The machine speeds up, and the induced voltage increases until the balance between the rectifier output voltage and the inverter counter EMF VD is restored. And in a wound field motor, usually the field is also controlled below the base speed to maintain the constant flux. For a wound field motor, speed control of a base speed is obtained by reducing the field current. A decrease in field current reduces the induced voltage and hence the inverter counter MFVD, and therefore ID and machine torque increase. And the increase in beta has an adverse effect on the power factor. So because the poor power factor and high terminal voltage, both copper loss and core loss become large and efficiency decreases. Coming to power factor optimization, so in a motoring operation, the power factor is maximum when beta is minimum or alpha is maximum. So at a minimum beta, the inverter output voltage is maximum. Consequently, the power transferred from the DC link to the machine for a given value of ID is maximized, and minimum value of beta is obtained when the margin angle is chosen, just sufficient to ensure safe commutation. So the minimum value of beta is beta minimum equal to mu plus gamma minimum or gamma minimum equal to kq omega tq, where kq is a safety factor and maximum power factor is given as pf max equal to cos and beta bracket beta minimum minus 0.5 mu equal to cos gamma minimum plus 0.5 mu, or cos mu plus gamma minimum equal to cos gamma minimum minus 2 omega LCID upon root 6, which is V. Now coming to inverter control strategy for load commutation. So a number of approaches are possible for inverter control. If we commonly use control strategy are described here, like constant margin angle control, constant commutation lead angle control, constant no load torque angle control, commutation lead angle varying linearly with ID, no load torque angle varying linearly with ID. So coming to constant margin angle control, operation of the inverter at the maximum safe value of the margin angle, give the highest power factor and the maximum torque per ampere of the armature current. This allows the most efficient use of inverter and motor both. So exact implementation of this constant is not possible because the minimum value of the commutation lead angle cannot be accurately predicted. So thus this control strategy is implemented only approximately. So even then it requires a complex control. The control strategy can be implemented using rotor position encoder and thermal voltage sensing method. Constant commutation lead angle control. A simple control is obtained when the inverter operates at constant commutation lead angle beta. So cos beta minimum equal to cos gamma minimum minus k ID upon Im dash, where k is the constant and beta minimum has the highest value when the ratio has the maximum value, that is ID upon Im. And when the operation is limited to the base speed, beta minimum has the highest value and ID or torque is maximum. So coming to constant commutation lead angle control, this control ensures commutation at all operating points. In addition, machine will still operate at the highest power factor at maximum torque, and power factor and efficiency will be lower for low torque due to a decrease in mu compared to the constant control at constant margin angle control. So for above base speed at a constant terminal voltage, beta has to be maximum value when the machine operates at maximum ID and speed. So this control scheme offers a performance which is inferior to the constant margin angle control but better than the constant load angle control, which is discussed in the next slide. So coming to constant no load torque angle control, in this scheme the drive operates at constant no load angle delta dash OC, and delta SOC is to provide enough commutation margin at the highest value of ID. This will ensure safe commutation for lower value of ID. So constant commutation lead angle control offers a performance which is better than the constant no load torque angle control but inferior to the constant margin angle control. In this control scheme, the drive has low power factor and efficiency at lower values of ID, and this control scheme and constant commutation lead angle control give increased torque pulsation at low speed. So there are some other control scheme in next which provide compromise between the complexity but the excellent performance and the simplicity but poor performance of the above discussed control strategy. So coming to commutation lead angle varying linearly with the ID. So value of commutation lead angle is given by beta equal to gamma minimum plus kb ID, where kb is the suitable region to make enough margin angle available at all operating points. So the value of no load angle control with varying, the value of load angle given by delta 0 dash equal to delta om dash plus k delta ID. Here delta om dash is the value of the torque angle which provides a margin of gamma minimum for ID equal to 0. Thus the value of k delta is chosen to provide the sufficient margin angle for all operating points. So coming to merits and demerits of load commutation. A load commutated inverter has low cost, weight, volume and losses as compared to force commutated inverter, and the synchronous motor drive with low commutated inverter are widely used in high power applications. So the attainable frequency range of load commutated inverter is larger than the force commutated one, as it depends on the commutating inductance and turn off time of the inverter thyristor. So when the operating above the base speed at constant induced voltage, the power factor does not become too low because of the large value of mu. At very low speed, the load commutation is unsatisfactory as it is due to induced voltage which is low. Therefore, below 10% of base speed, load commutation cannot be used. And this is typically cycloconverter with load commutation. So this cycloconverter consists of 3 dual converter A, B and C, each commit consisting of the 2 3-phase pulse control rectifier, and during the positive half cycle of phase current I, B, IC, the machine draws current from rectifier A plus, B plus, C plus respectively, and during negative half cycle, rectifiers A minus, B minus, C minus respectively. Therefore, the conduction sequence in pairs shall be A plus, B minus, A plus, C minus, B plus, C minus, B plus, A minus, and C plus, A minus, and C plus, B minus. So the load commutation is mainly used to change from one pair to another, and the commutation process is identical to the current source inverter already discussed in the previous slide. So at low speed, the machine induced voltage are too small to cause the transfer of current from one rectifier to another, hence the source voltage is used to affect this commutation. So the main advantage of load commutation in the cycloconverter is that the output frequency can be higher than the AC supply frequency, thus providing a speed control over a wide range. Now coming to operation of a wide field synchronous motor drive from a variable frequency current source. So the basic control strategy of synchronous motor is to operate the machine preferably at constant flux below base speed and at reduced flux and constant terminal voltage above base speed. At a variable frequency control synchronous motor with self-control essentially work as a commuterless or brushless DC motor. However, the synchronous motor control is not as simple as that of a DC motor, mainly because unlike a DC motor, the synchronous motor operates without eliminating the armature effect. So the flux does not depend on the field current but also on the armature current. So further, the additional requirement related to the power factor impose additional constraint on the drive operation and control, and the flexibility of field control in a wound field synchronous motor makes it suitable for simultaneous control of flux, power factor and speed. However, in a permanent motor, either power factor or flux can be controlled along with the speed. So armature current in a control to vary torque and speed during low base speed operation, and the field current and torque angle are controlled to maintain constant flux and desired torque. At base speed, the terminal voltage either saturates or reaches the rated value. So therefore, above base speed, the field current and torque angle are controlled to vary flux inversely the speed and to maintain the power factor at the desired value. So coming to operation at unity power factor, to drive fed from a variable frequency current source may operate at leading power factor when load commutation is used. Otherwise, it may operate at unity power factor to maximize the use of source and motor rating as to avoid minimize the losses. Now, if IS is increased, to increase torque, IF dash and delta dash should also be controlled simultaneously to maintain IM constant. So at unity power factor, constant flux operation below AC speed is obtained by keeping IM dash constant at rated value, and the phase diagram of unity power factor case is shown in next slide. So this is typically for motoring and braking for typically from phasor diagram, IF dash cos delta equal to IM and IF dash and delta equal to plus minus IM. Operation at unity power factor, where IM is typically either in phase with the voltage or IS in phase with the voltage or out of phase with the voltage for braking. So coming to mathematical analysis for operation at unity power factor from the phasor diagram, IF dash equal to under root IS square plus IM square. So delta equal to plus minus tan inverse in bracket IS upon IM, and delta dash equal to plus minus in bracket 90 plus delta absolute value of delta plus minus 90 plus tan inverse IS upon IM, where positive sign is for motoring and negative sign for braking. IM is the rated value of IM dash, hence it can be seen that if IF dash and delta dash are varied as a function of IS, then the machine will operate at a constant flux and unity power factor below base speed. So torque is T equal to 3 by 2 P LS IS IF dash sin delta dash, and where LS is the synchronous inductance, it can be written as T equal to plus minus 3 by 2 P LS IS IM. So from the torque expression, it can be concluded that the torque is proportional to armature current and is independent of frequency or speed. So torque has a constant value when operates at a maximum permissible current and above the base speed when the per unit frequency A greater than 1, V is held constant. Hence, the magnetizing current must be reduced to IM upon A. Therefore, IF dash equal to root IM IS square plus IM upon A square, or delta dash equal to plus minus 90 plus tan inverse A IS upon IM. And it is difficult to implement previous strategy. So as IF dash and delta dash are functions of IS and frequency both, so since the power PM equal to 3 Vs Is at unity power factor. Therefore, with constant V, the drive operates in constant power factor mode. The various variations of T, V, If dash and Im with per unit speed is shown in the next slide for motoring operation at constant Im. So you can clearly see how with the frequency or speed, the torque, voltage, stator current, your typically field current, magnetic current, and the voltage vary. Operation at leading power factor. So drive fed from a load commutator inverter or cycloconverter operates at leading power factor, and the constant margin angle control is required only during the motoring when the machine side converter operates at inverter. For braking, beta can be set at 180 degree. For all operating point, the phasor diagram of synchronous motor fed by load commutator current source inverter is shown as typically here. So you can clearly see here that it operates at leading power factor. So from the phasor diagram, mathematical analysis operation, so If dash equal to under root I square plus Im square minus 2 Is Im cos 90 plus mu equal to under root I square Im square plus 2 Is Im sin phi, and from Im upon sin 180 minus delta dash equal to If dash upon sin 90 plus phi, and If dash sin delta dash equal to Im cos phi, and delta dash equal to sin inverse Im upon If dash cos phi. Therefore, the torque equation T equal to 3 by 2 Ls into Is dash sin delta dash, and it can be written as T equal to 3 by 2 Ps into Is Im cos phi. So from the torque equation, it can be concluded that at constant power factor angle, the torque is proportional to armature current and the power factor is proportional to speed. However, the available torque is reduced by a factor of cos phi compared to unity power factor operation. So therefore, the power factor shall be as high as possible or operation at lowest possible value of phi, that is with the constant margin angle control. All these are for operation for below base speed, and for operation above base speed with the constant phi, mathematical expression can be derived by substituting Im upon A for Im in the various equations. If dash equal to Is square plus Im upon A square plus 2 Is Im upon A into sin phi. So delta dash equal to sin inverse Im upon A If dash cos phi, and torque is 3 by 2 Pls Is Im upon A to cos phi, and Pm equal to 3V cos phi into Is. So therefore, if a given power factor, the motor operates in constant power mode. So equation for constant margin angle below base speed are If dash equal to root Is square plus Im square plus 2 Is Im sin bracket 0.5 mu plus gamma mu, and delta dash equal to sin inverse Im upon If dash cos 0.5 mu plus gamma minimum, and therefore torque is T equal to 3 by 2 Pls Is Im cos 0.5 mu plus gamma minimum. So the equation for constant margin angle control over base speed are obtained. If dash equal to under root If Is square plus Im upon A square plus 2 Is Im upon A sin 0.5 mu plus gamma mu, and delta dash equal to sin inverse Im upon A If dash cos 0.5 mu plus gamma minimum, and therefore power equation P equal to 3Vi cos 0.5 mu plus gamma minimum. So operation of wild field synchronous motor from a variable frequency source voltage source. So operation at leading power factor. So in variable frequency voltage source, also machine operates at a constant flux below base speed and at a constant turn voltage above base speed. The additional flexibility made available by the field current control is used to control the power factor, and it is preferred to maintain power factor at unity, and motor operates at unity power factor below base speed. So If dash cos delta minus Im equal to 0. So thus If dash will be varied with the delta accordingly. If dash equal to Im upon cos delta. The power input to the machine given by Pm equal to 3 Vis and T equal to 3 by 2 Vis, or equal to 3 P upon 2 omega Ls Im Is into 3 P Ls upon 2 Im Is. Thus at unity power factor operation, the armature current varies linearly with torque. So for given armature current, the torque has a constant value at all speed, and the motor operates in the constant torque mode, and above the base speed V is held constant. Therefore, Im dash equal to Im upon A, and for unity power factor operation, If dash equal to Im upon cos delta, Im upon A cos delta. So therefore If dash is changed as a function of beta and speed and power. So Pm equal to 3 Vi as such. It shows that the machine operates in constant power mode above base speed. And thank you.